Hello friends, and welcome to another sleepy science journey. Tonight, we follow a quiet pull stitched into the dark between galaxies. No thunder, no rush, only a gentle lean in the fabric of space. The Milky Way drifts with it, and we listen for where that hush is guiding us. Some truths don't whisper, they redraw the map. Our galaxy isn't wandering, it's being steered by a hidden mass district. Instruments keep catching the same fingerprint, a slight temperature contrast in the ancient glow. Across the sky, thousands of galaxies lean that way, as if space itself is sloped. The route slips behind our dusty midplane, where ordinary light fails but radio slips through. X-rays show heat, and distance ladders keep agreeing. There's no single monster waiting there. It's a layered province of gravity, deeper than any one cluster. We call it the Great Attractor, the reason our cosmic compass points through darkness. We'll uncover these signs one by one, in a calm, soothing style. There is a steady motion beneath everything we know. Galaxies change position without sound, carried by the sum of countless pulls. Our own Milky Way is not drifting by chance. Its speed is measurable against a universal backdrop, a faint microwave afterglow that fills all directions with near-perfect uniformity. Within that glow, there is a slight temperature contrast that reveals we are moving. The numbers are small in temperature and large in consequence, because they give us a frame to speak about motion that does not depend on any one star. Astronomers learn to subtract local movements. The rotation of Earth does not help here, nor the orbit around the Sunday. Even our path around the center of the Milky Way is accounted for. After these corrections, a remaining velocity persists. It points toward a swath of sky that is inconvenient to see, blocked by the dust and gas of our own disk. Observers often call it the Zone of Avoidance, a region we avoid not from fear, but because the light is hidden there. Behind that curtain, the pattern of galaxy speeds suggests a deeper structure. Surveys with radio telescopes and infrared eyes find what optical maps miss. Galaxy clusters gather where gravity has had time to act, and clusters themselves fall toward larger concentrations. When positions and velocities are combined, a flow appears. The vectors are not random. They trace toward a region where mass is layered through space on scales larger than any single cluster can explain. To describe that region, astronomers use a practical name. They call it an attractor, because galaxies toward it have speeds that exceed the average expansion. The label does not imply a single object. It marks a center of gravitational influence, spread across tens of millions of light-years and more. In some reconstructions, a prominent cluster, known for its richness, sits near the flow's focus. In others, momentum continues past it toward even larger structures. All of this can be explained with ordinary gravity acting over extraordinary time. The universe expands on average, yet local overdensities reshape paths. Where matter accumulated early, galaxies followed steeper gradients. Where dust hides those gradients, different wavelengths fill the gaps. The picture improves when distance indicators are calibrated, and when subtle differences in galaxy brightness are turned into speed estimates. This is a story about how motion reveals mass. It is also a calm recognition that not every destination is reachable. Expansion accelerates. Bound things remain. Unbound flows stretch away. If you are listening at night, let the facts arrive without hurry. Each one holds a small weight. Each one connects to the next. Settle into that quiet chain and drift with the idea of a pull we can measure and a horizon that moves as well. Dust along our plane dims more than stars, turns a wide ribbon of the sky into a softer, hazier band where ordinary starlight struggles to pass. The band is not uniform. Some stretches are thin and gauzy. Others are packed with grains and cold clouds. Through those thicker lanes, distant galaxies fade, and early sky catalogues missed them. That absence was a measurement artifact, not a true emptiness. When astronomers tuned their instruments to radio wavelengths around 21 centimeters, another picture opened. Neutral hydrogen inside far-off spirals sang on that frequency, slipping through the dust with ease. Infrared cameras added another layer by tracing the steadier glow of old stars, whose light is reddened less by grains. Switching wavelengths turned a wall into a window. Once galaxies reappeared behind the plane, the question shifted from counting to understanding motion. Redshifts alone tell part of the story. In an expanding universe, more distant systems show larger shifts because space itself stretches the waves. That recession provides a baseline at each distance. On top of it sit deviations that come from local gravity. Those deviations are peculiar velocities, the signature of mass nearby tilting the flow. By collecting these remainders over many directions, a pattern emerges. When those remainders lean the same way through the dusty band, the direction is not random. It marks an area of stronger pull hidden in ordinary light, yet obvious in motion. Large dishes in southern latitudes became crucial because the relevant constellations pass high there and low in northern observatories. Long surveys swept the plane, storing millions of narrow radio spectra. Each detection held a rotation clue, a distance estimate, and a point on the sky. Infrared sky maps from spacecraft later filled gaps with uniform coverage, so the band near the plane no longer acted like a gash. Redundancy mattered. Independent techniques rarely converge by accident. Agreement gave confidence that the flow was not a local mirage tied to our neighborhood. It extended across volumes with thousands of galaxies, all influenced by a common gradient. The geometry traced by these motions is not a simple corridor. It curves like an archway, guiding streams that bend as they pass. Within that curve sits a rich cluster in projection, its galaxies moving fast inside a dark matter halo that outweighs the stars many times over. X-ray glow from hot intracluster gas confirms a deep potential. Weak lensing of background galaxies adds mass without caring about light. Yet when astronomers compare the cluster's mass with the speed of the flow, the numbers do not close. The observed drift is stronger than one node can explain. The arch hints at layered structures, mass behind mass, a sequence of ridges that together steepen the descent. This is how a chart of what was missing becomes a map of what matters. Where visible light fails, radio and infrared step in. Where counts alone deceive, velocities confess. The plane hides, but only from certain eyes. With the right frequencies and careful calibration of distances, the band becomes navigable. Dust reddening is modeled and subtracted. Star crowding is handled with pattern fitting that pulls galaxies out of glare. Hydrogen profiles are corrected for inclination so rotation widths can be trusted. Each correction brings a cleaner remainder, and each remainder sharpens the direction. As the dataset grows, the corridor's curve sets the tone. Foreground lanes of gas and dust soften the edges of the view, while not changing the underlying pull. The arch does not end at the prominent cluster. Flow lines bend around it and continue toward deeper longitudes. Those longitudes host more mass than early maps could see. They hold other clusters and knots, spread across distances where expansion is stronger, yet still close enough to leave fingerprints in peculiar speeds. The influence is cumulative. Nearby, overdensities tilt paths. Farther ones add their own small lean. Over hundreds of millions of light-years, those small leans add up. It is natural to want a single cause and a tidy finish. The sky refuses that simplicity. The hidden corridor is a composite structure. It connects our side of the plane to districts beyond through a chain of gradients. Gravity follows those gradients without concern for our naming. When we say attractor, we mean the net effect of many contributions aligned in one general orientation. The word is convenient, the field is continuous. The steadiness of that continuity is comforting in a sleepy hour. A listener can let the numbers pass like distant road signs, while the route itself remains smooth. There is no need to rush for a destination. The point here is to feel the shape of a path that becomes clearer when we change the light in which we look. A path that points onward even when the window is narrow and the view is soft. Across the whole sky sits a faint afterglow from early times. Its brightness is almost uniform, with tiny speckles that record differences in density when the universe was young. Laid atop those speckles is a larger smooth tilt, slightly warmer toward one direction, slightly cooler toward the opposite. That tilt is not a relic of the first light, it is our imprint upon it. When a detector moves through a bath of radiation, waves ahead are compressed a little, and waves behind are stretched. The tilt's amplitude and angle become a speed and a bearing. Few tools in cosmology offer a reference so universal. It is not tied to one star or one cluster. It fills every direction at once. To turn that sky-wide indicator into a picture of our region, we begin by taking out motions that are close to home. The spin of our world is known well enough to be removed precisely. The yearly path around our star is modeled and subtracted. The longer drift of the Sun around the galactic center is accounted for using the best measurements of local stellar orbits and the shape of the Milky Way's potential. After these are removed, a residual remains. It points toward longitudes where our own dust is a nuisance. On its own, this residual certifies motion, but not its cause. Causes are rebuilt by comparing observed redshifts with distances measured independently of redshift. The difference between the expected expansion speed and the observed recession gives a peculiar velocity along our line of sight. Those independent distances come from several ladders that rely on simple, robust relations. In spiral galaxies, wider neutral hydrogen lines mean faster rotation, and after calibrations, brighter total light. Observed brightness, corrected for dust and inclination, yields distance. In smooth elliptical galaxies, small grainy variations in their surface light act like a texture scale. Closer galaxies show coarser granulation. Farther ones appear smoother. Calibrated with nearby anchors, those fluctuations become rulers. Certain variable stars and sharp features in the color magnitude patterns of old populations tie the nearest rungs. Type-specific supernovae carry the ladder farther when hosts are already anchored by closer methods. No single yardstick is perfect. Together, their errors point in different directions, and agreements become meaningful. As distances accumulate, the velocity field takes shape. Vectors traced from many galaxies lean toward a region near a rich cluster, and then continue into deeper coordinates. It is tempting to treat that cluster as the sole magnet and end the story. The data resist. The region of maximum pull is broad. It contains the cluster, but also neighbors whose mass is not negligible. Behind them lies another district, more extensive, whose long reach nudges even dense nodes. Motion on these scales is layered. Small dark halos govern the dance inside galaxies. Cluster halos guide groups. Overdensities spread across supercluster scales shift entire sheets. The background tilt provides direction. The ladders provide depth. Combined, they explain why our present speed relative to the afterglow owes more to architecture than to any one anchor. This does not break the idea of expansion. Think of expansion as the slow breathing of space and the peculiar flow as the breeze riding on that breath. The breeze changes direction with valleys and ridges. The breathing continues beneath it. All of this connects to human feeling in a quiet way. A person finds calm when there is a steady frame to lean against. The afterglow offers that steadiness for motion on the grandest scale. It keeps time without clocks and keeps direction without signposts. Against it, our local corrections feel like clearing small obligations before recognizing the wider pull. Removing the spin, the orbit, the drift is like tidying a desk before reading. When the desk is clear, the page is easier to see. Here, the page is a map of speed vectors that agree more than they argue, and their agreement is soothing in its consistency. As the tide of measurements improves, the bearings stabilize. Parallax sets the 0 point for nearby anchors more cleanly. Radio interferometers sharpen the 21-centimeter line widths. Infrared arrays reduce errors in crowded parts of the plane. Each improvement peels away noise that could mislead the remainders. The frame does not waver. It continues to say we are in motion, and that our motion points toward a complex region whose shape is still being drawn. The simplicity of the tilt and the complexity of the cores live side by side. That pairing fits the tone of a soft night. One hand rests on a fixed rail. The other traces gentle curves on a map that spreads farther than any single lamp can reach. Closer to home, we live inside a small assembly with a few large spirals and many smaller companions. Their mutual gravity threads the neighborhood together. Over long spans, the two largest members will interact, trading angular momentum and stirring gas that will form new stars. Today, those internal motions matter less to our speed against the afterglow than the region beyond. The center of mass of our little assembly is drawn toward a richer cluster, a modest distance away. That is expected. Clusters represent the heaviest bound structures, where thousands of galaxies orbit inside a shared dark halo and hot gas settles into equilibrium under pressure and gravity. Between our group and that cluster run filaments with higher than average galaxy density. Redshift surveys plot them like strands. Their lines are clear when three-dimensional positions are shown. Along those strands, material has streamed for billions of years, responding to slight overdensities that have grown slowly into present walls and knots. At the places where several filaments intersect, clusters thicken. In the quieter volumes between, space is underdense, and galaxies are rarer. Those hollows do not push by themselves. They reduce pull from their direction, tipping paths toward the lanes. Inside the prominent cluster that influences our path, member galaxies have high internal speeds. Spectra measure those speeds, and simple relations between dispersion and mass convert them into a deep potential. X-ray maps of the cluster's hot atmosphere confirm the depth through temperature and brightness profiles. Weak lensing bends background shapes by a small amount that tells the total mass. These point to a halo far heavier than the light alone would suggest, a standard signature of dark matter. Infall toward this node alters the peculiar velocities of groups between us and it, but the pattern does not end there. Flow lines bend around the node and keep leaning into coordinates farther along the pose, dusty plane. Beyond those longitudes lies another concentration, not tidy and singular, but layered with several rich clusters set deeper into space. Their combined influence extends across vast spans. Even regions already crowded feel a subtle lean toward that district. This is why peculiar velocities remain significant after accounting for the nearer node. Gravity's bookkeeping is cumulative. Each overdense patch adds something. The sum grows across tiers until acceleration begins to erode leverage at very large ranges. No unfamiliar physics is needed. Ordinary gravity integrates small contrasts into big consequences over time. A modest excess spread over a huge volume biases motion in ways that are measurable. That bias scales with distance until the background's acceleration reduces what can still be gathered. Inside that threshold, attraction shapes roots. Outside, expansion imposes its broader rhythm. Our path, then, is the result of neighborhood settings, corridor curve, and deeper district. When people say attractor, they compress all of that into one word. In practice, the road is an average through many subtle descents. There is a human echo in this layered map. Near concerns anchor daily life. Larger obligations tilt the longer course. Far possibilities color the horizon without dictating the next step. Each scale leaves a mark on motion. Each scale is real. Listening at a slow pace, a person can let the structure settle without needing a list of names. Filaments, walls, clusters. Each is a way of saying that matter has gathered unevenly, and that unevenness guides everything that moves. As the night continues, the main comfort is that guidance is steady, and complexity does not break the calm. It simply adds texture to a direction that remains coherent across many measures. Positions of galaxies on the sky are recorded with precision. Their speeds along our line of sight are measured from spectral shifts with small uncertainties. What is harder is to infer full three-dimensional motions for many galaxies at once, and to imagine how those motions arose from an earlier, smoother pattern. One practical approach treats the present distribution as the result of transporting mass from a simpler arrangement under gravity's rules. If one asks how to move matter from an early, near, uniform field into the observed web while obeying those rules and paying the least cost, a plausible path emerges. This is not guesswork dressed as poetry. It is a computational exercise with clear inputs and constraints. The inputs are present positions and line-of-sight peculiar velocities where available. The constraints come from the statistics of the early fluctuations seen in the afterglow, which limit how uneven the starting field could be, and from the requirement that gravity and expansion guide the evolution. The output is not a single film of history, but a family of histories that fit within uncertainties. Errors grow with distance and with how far back one tries to step. Yet within a few 100 million light-years, the reconstructions are stable enough to be useful. When such reconstructions are run on volumes around us, coherent streams appear. They avoid hollows, trace along lanes, and converge near denser knots. One strong convergence lies near the rich cluster hidden by our dust. Past that bend, flow lines curve toward the deeper district whose mass inventory is larger. The model's value is not merely confirming destinations suspected from counts. It quantifies how much each scale contributes to our present peculiar speed. Shares can be assigned, a portion from the nearer node, a portion from the deeper complex, and a remainder from intermediate walls that guide the route. These shares change slightly as data improve. When distance ladders are recalibrated with better parallax, or when radio surveys add fainter galaxies near the plane, the partition shifts by small amounts. The trend holds. No single actor accounts for the whole. The attractor is best described as a regional feature of the mass field, not a solitary beacon. That phrasing matters because it shapes expectation. A regional feature can steer without promising eventual arrival. It can be stable in the present, yet evolving at its own pace, influenced by even larger scales. There are limits. At great distances, small observational errors blossom into large uncertainties in paths. Beyond a certain look-back, the assumption that simple growth is a good description breaks down because non-linear interactions become dominant. The reconstructions respect these limits, and report uncertainties that widen where they must. Within the range that matters for our measured motion, the maps are steady. They justify speaking carefully about influence rather than destiny. The calm here is in the method's patience. It takes what is known, acknowledges what is not, and joins them with rules that have been tested in many other settings. The result is a landscape of currents viewed from above, a diagram of where paths are likely to go when left to the pull of accumulated mass. For a sleepy listener, that picture is enough. It needs no flourish. It asks only for trust in measurements repeated many times, and in a law of attraction that has held from the scale of apples to the scale of clusters. The currents glide where the field is low, and we glide with them. Near the focus of our velocity field sits a cluster so far that its galaxies are faint points in modest telescopes. Its total mass is read in several independent ways. The speeds of member galaxies inside it, measured from spectral lines, provide a dynamical estimate through simple relations that tie dispersion to the depth of the potential well. Hot plasma trapped by that well shines in X-rays. Its temperature and surface brightness inform how deep the well must be. Behind the cluster, background galaxies appear subtly sheared. That weak lensing measures mass, without asking how much light the mass emits. All these lines of evidence converge on a value many times larger than the sum of starlight, a standard result for these structures. Faced with that weight, it is easy to think the story ends here. A cluster this massive can deflect the paths of many neighbors. It sits close to the direction indicated by our peculiar motion. It shapes flow lines approaching from our side. Even so, when predicted infall speeds are compared with velocities measured in groups between us and the cluster, the totals fall short. The shortfall is not dramatic, but it persists across catalogs and methods. The implication is that mass beyond the cluster adds another grade to the descent. The bend is real, and the slope continues. Deeper surveys confirm that the background is not mild. Farther along the same general bearing lies a district crowded with multiple rich clusters. In redshift space, it looks like a raised plateau rather than a single peak. X-ray maps show several hot atmospheres near one another. Counts corrected for foreground dust rise toward its coordinates even when optical confusion is severe. Where weak lensing measurements exist, the shear pattern tracks an extended halo of mass. Flow reconstructions translate those maps into motion. Vectors approach the nearby cluster, twist gently, and align toward the deeper district, as if a river met a wide lake on its way to a larger basin. This layered picture solves two puzzles. It explains why the nearby node is bright in X-rays and strong in lensing, yet still insufficient alone to account for the measured speeds. It also aligns the direction and amplitude of our peculiar motion with the combined pull of structures along the line. The attraction is distributed. The closer node is a staging point. The deeper district adds momentum. Intermediate walls smooth the curve. As distance ladders are checked against new parallax baselines, and as plane crossing surveys gain sensitivity, the fit tightens. The cluster at the bend will not lose its role. It sits where lines of influence knot, and its presence guarantees that flow lines swing around it. Naming it as the entire cause, though, would be a simplification that erases the contribution of neighbors. Gravity is additive. It cares about gradients over scale. That is the quiet lesson of this bend. Influence is shared, and the route honors each share. For someone listening in a soft hour, there is a gentle comfort here. The world does not need one hero node to make sense. Multiple actors act together without noise. Measurements agree enough to guide, and doubts remain small enough to hold. The map is slightly blurred at the edges, where dust thickens and distances stretch, but the center holds firm. The river keeps its direction, even as it widens into a lake and finds a deeper basin beyond. There is no hurry in this movement. The story is gravity working over long time against a background that expands. Each step of understanding is methodical, each conclusion modest. That modesty fits the tone of a night built for rest, where certainty is not loud and complexity is not sharp, and where a bend in the current is simply another way to continue. Farther along the bearing set by our measured drift, wide surveys reveal a deeper assembly that does not behave like a single, clean-edged halo. It appears as a crowded district where several rich clusters occupy neighboring volumes and partly overlap in projection. Their combined mass forms a gravitational basin, broader and lower than any one cluster could excavate. Member counts are high across many nodes in that district. Internal galaxy speeds inside those nodes are also large, which signals long growth fed by converging filaments. The district is set beyond the nearby bend identified by earlier flow maps, yet its cumulative pull still registers here as a steady lean in peculiar velocities. Evidence for that reach arrives from multiple independent datasets. Velocity fields built from distance indicators tilt more strongly when this complex is included in the modeling. Galaxy counts that correct for dust and crowding rise toward its coordinates, even in sky zones that are difficult for optical work. X-ray maps display several hot halos gathered in a patchwork, consistent with a packed region where intracluster gas sits in deep wells. Where weak lensing measurements are available, the shear pattern traces the sum of mass without regard to how brightly any single component shines. Taken together, these views support the same interpretation. Beyond the first wall of structure, an extended basin of mass deepens the regional gradient, and that gradient adds measurable guidance to our present motion. Its effect on our path is not absolute, because distance matters. The farther a structure lies, the more the global expansion separates it from us, and the late-time acceleration weakens the time available for distant tugs to translate into completed infall. Even so, within the range where gravity can weld flows across filaments and walls, the district contributes a meaningful share of our peculiar speed. It also tugs on nearer nodes. The rich cluster at the bend is slightly drawn toward the deeper basin, and that shift deflects neighboring streamlines in our direction. Influence is both direct and indirect, layered across scales. Uncertainty remains in the full inventory of mass beyond this district. Map edges are not physical borders. They are limits of current surveys and of the distance calibrations that feed them. As those limits are pushed outward, the share we assign to each contributor may shift by small amounts. The larger conclusion is robust. The attractor is not a point with a neat address, but a graded valley whose slope continues into coordinates we are only beginning to chart. That slope explains why our measured motion cannot be assigned to a single doorstep, and why vectors bend smoothly rather than snapping toward a lone anchor. It is easy to picture a finished route toward a fixed destination. The universe on these scales does not provide that closure. The basin toward which we lean is itself in motion relative to larger districts, and the background acceleration reduces the time budget for mergers far from home. The path lengthens while the cosmic clock pulls in the opposite direction. Bound regions complete their assembly. Unbound regions separate. Our direction holds, yet the far shore recedes from the category of events and resides more comfortably in the category of causes. The district's geometry matters for how motion threads through it. Several massive nodes sit along intersecting filaments. Between them, smaller groups flow along lanes that behave like channels with gentle banks. When flow reconstructions are sampled at different smoothing scales, the same general descent appears. Vectors feed into the district, from multiple approaches, pass near local wells, and continue toward the deepest part of the basin. This pattern explains why our peculiar velocity can be decomposed into portions tied to different tiers. It also clarifies why the near bend is prominent in many maps, while still being insufficient by itself. The deepest share accrues from long slopes along walls that shape the approach. X-ray observatories provide temperature maps of the gas trapped in the wells of several clusters in the district. Higher temperatures indicate deeper gravitational potentials. Those temperatures line up with mass estimates from galaxy dynamics and from lensing. Infrared surveys catalog old stellar populations that trace the backbones of member galaxies, even where dust complicates optical counts. Radio surveys detect neutral hydrogen in gas-rich spirals skirting the edges, which helps build distance catalogs less affected by stellar crowding. Each wavelength adds a separate argument. None depends on the same set of errors. Together, they form a coherent field in which the deeper district emerges with clarity. The expansion rate is not merely a background number, it is the frame within which gravity must work. At the distances involved, the pure expansion component of redshift is large, and peculiar motions are the differences we recover after careful subtraction. The fact that those differences maintain a consistent direction across techniques is itself a strong signal. It means the deeper basin's influence is not an artifact of one catalog or one correction. It survives cross-checks, recalibrations, and alternative ways of slicing the data. When counts, temperatures, shears, and velocities agree on the same tilt, the slope is real. It is not a sharp pull felt only by a few groups. It is a broad incline that stretches across lanes and remains visible when data are sliced in different ways. For a calm listener, the important feeling is steadiness rather than urgency. The map is big, and the changes we infer are slow. We are not racing toward a finish. We are reading a gentle incline. The incline is built from mass that took billions of years to pile up, and from voids that grew emptier as matter drained away along lanes. Over that time, the district's breadth became its strength. A wide basin gathers more softly but more persistently than a single narrow well. That softness matches the way our peculiar speed appears, not as a sudden lurch, but as a long persuasion that bends roots with patient consistency. As instruments improve, the picture will sharpen. Shear maps will be cleaner, X-ray temperatures more precise, and plane crossing catalogs richer. Each refinement trims uncertainty without changing the need for a broad, heavy district beyond the first wall. All of this leads to a quiet conclusion, well suited to rest. The deeper district beyond the first wall is not a dramatic singularity. It is a broad, heavy countryside of structure whose combined presence guides our motion in the present epoch. It does so both by pulling directly and by drawing on nearer nodes that pass along its influence. Its distance limits what can ultimately be joined, especially in an era when expansion accelerates. Yet its role in setting our current direction is secure. The basin is large enough and its walls high enough that flows entering its vicinity are biased along the same general bearing. That bias explains the lean we recover after subtracting expansion and local spins. It also aligns with the way clusters within the district are slowly sliding relative to one another, rehearsing internal fusions that will proceed even if the wider field can no longer close the gap on still larger scales. A listener need not memorize the names of the nodes. The message is simpler. Beyond the first wall lies a heavier country, and that country shapes how we move. There is also the bookkeeping of biases that hide inside large compilations. Samples that favor brighter galaxies at larger distances can overstate average speeds, if not corrected, a tendency known to survey designers. Analysts counter this by modeling completeness as a function of flux, and by comparing subsets selected in different bands. Near the plane, star, crowding, and patchy. Extinction can inflate uncertainties, so teams lean on wavelengths less troubled by dust and on statistical methods that downweight confused fields. These safeguards do not erase the signal from the deeper basin. They keep the main signals from being invented by the pipeline. Another subtlety is covariance. Errors in distances and errors in inferred peculiar velocities are not independent. A shift in one can bias the other. Modern reconstructions incorporate this linkage explicitly, propagating uncertainties through to the final maps and reporting how sensitive each structure's assigned share is to those inputs. When the deeper basin remains necessary across reasonable changes to assumptions, confidence grows that it is a genuine feature of the mass field and not a quirk of a particular calibration. What we carry away, then, is a measured landscape. The near bend is real, and so is the broader basin beyond it. The edges of our current maps are soft but improving. Gravity's guidance is cumulative and patient. The basin's pull will continue to shape our orientation, even if the far merger it suggests cannot complete. In a quiet room, it helps to think of the district not as a destination but as a gentle grade underfoot. We move because the ground tilts that way, and the tilt remains, steady and kind, across the distances we can measure and the times we can imagine. It remains steady when astronomers place measured galaxies into 3 dimensions. A quiet order shows itself. Long lanes of systems thread across volume and meet at broad crossings that hold many members. Flat sheets span between these lanes like gentle terraces. Where several strands intersect, clusters thicken into busy knots. Where strands thin away, wide tracks hold fewer galaxies for long stretches of distance. This arrangement is the cosmic web. It is not drawn by hand, and it is not an illusion of projection. It reflects how matter settled within gravity over long ages, guided by small differences that grew into visible structure. The map comes from redshift surveys that record positions for vast numbers of galaxies, and from distance measurements that anchor the scale. Together, they turn a swarm into a chart, and the chart into something we can trace with calm eyes. The web carries a rhythm that began long before any galaxy formed. In the early universe, ordinary matter and light were tightly coupled. Pressure waves traveled through that medium, expanding outward from small seeds. They did not run forever. When the environment cooled enough for atoms to appear, radiation and matter went their own ways. The waves stopped moving, but each left behind a mild preference in spacing. The imprint is tiny when stated as a fraction. Yet over cosmic time, that faint bias helped determine where matter gathered most efficiently. The result today is a slight favoring of certain separations between pairs of galaxies. It is a memory, written into distance, of sound in a younger sky. Observers look for this memory using statistics rather than pictures. They count pairs by distance and search for a small excess near a particular range. The excess is not dramatic, but it repeats across independent catalogues and instruments. Its presence acts like a gentle, reliable yard. It links modern maps to early conditions, giving a fixed reference when models of growth are tested. In our larger neighborhood, arcs of walls and placements of rich clusters appear in arrangements compatible with one of these echoes. The alignment does not give a perfect circle or an exact shell. It simply suggests that part of our surroundings still carries the spacing of that early pulse, and that suggestion helps when distance indicators grow sparse. The web is uneven by nature. Some sheets carry many groups and reach for long distances. Others are thin, with generous spaces between members and long, clear sightlines. Flow reconstructions use this unevenness to guide motion along paths of least Resistance. A group drifts more easily down a loaded lane than across a bare gap, because gravity is deeper where mass has already settled. This routing matters when we try to understand why our measured, peculiar velocity leans the way it does. The vectors do not aim for a single, clean dot. They arc across a landscape steered by the grain of the map. That grain is the texture of the web itself. These maps do not replace ways of weighing mass, but they strengthen them. A cluster's ability to bend background shapes is more compelling if the cluster sits at a multi-lane junction. A region where measured velocities are large is more credible if it lies downhill from surrounding sheets. In that sense, the early echo of pressure is folded into present motion. The faint spacing from a younger era provides a size scale that supports distance estimates, which in turn make peculiar motions possible to isolate. Gravity then reads the layout with no need for direction. Galaxies go where the field is lower, and the field is set by where matter has accumulated and where it has not. The web's architecture clarifies how influence is shared. Small dark halos keep individual galaxies intact and govern the speeds of stars within each system. Larger halos tie clusters together and explain the fast motions seen between their members. Between those extremes, sheets and filaments act as corridors. They escort many separate systems toward common districts without forcing them into one node. Our measured flow, then, is a sum of three kinds of guidance: the nearby pull inside halos, the routing along lanes, and the broader tilt from far over densities that bias whole regions at once. Each level is ordinary gravity acting over different scales, and each level can be seen in the maps. There is also a practical piece built into this picture. Observations inherit noise and bias. Some surveys favor brighter systems, others avoid crowded foregrounds. By checking whether the same strands appear across maps made from different samples, astronomers reduce the chance that a feature is an artifact. When a lane persists in catalogs built by separate teams, using different instruments and slicing by different properties, confidence rises that it reflects mass rather than method. That agreement makes the next step in any flow reconstruction steadier and makes the interpretation easier to rest upon. For a sleepy mind, this is a kind way to think about a huge subject. The web takes the idea of chaos away and replaces it with a structure that does not shout. It lets the listener imagine routes and neighborhoods. It shows crossings where many lines meet and explains why certain districts host more activity. And it hints that the calm echo from early sound acts like a dependable metronome beneath the map. That metronome does not force a rhythm on the voice. It only keeps time when we count distances and compare models. As maps improve, faint threads come into view. Small groups link to larger strands. Thin walls reach between sturdier ones. Each addition nudges the reconstructed routes with a touch more precision. None of this requires jargon to appreciate. It is enough to know that matter gathered unevenly and that motion responds to those differences. A traveler between galaxies would not find signboards. They would feel the gentle tug along a lane and a slower tug across a sheet. They would notice that open regions give little guidance, while rich intersections invite company. All of these elements feed into our understanding of the direction we measure against the background glow. The web is the stage, and the echo is the quiet beat that keeps distances consistent. Together, they give our route coherence without demanding a single, hard target. The flow arcs because the ground is shaped. Farther along that curve, other districts gather matter and lend their share to the tilt we detect. The story does not require drama. It asks only for patience, because the same structures that suggest our direction will hold their forms for a very long time. and so the web and the echo become a gentle support for the Great Attractor story, not a complication. They explain why influence is shared, why guidance bends, and why maps built by different means are able to agree. If a survey redraws a sheet, the change to nearby flow lines follows. If a new catalogue tightens a distance ladder, the position of a lane shifts by a small, predictable amount. Predictability is a quiet comfort here. It lets the mind settle, even as details improve. Matter arranged itself into strands and terraces. Early sound left a spacing that we can still find. Motion respects both. That is enough to carry the thought into rest. Between the crowded lanes of the web lie broad tracts, where the average density dips below the cosmic mean. They are not true vacuums. Small systems float there, and a thin haze of gas threads through. Even so, compared with the busy walls, these volumes hold little. When matter on the edges drifts toward richer neighbors, the centers of these tracts become emptier over long intervals. That continued evacuation has a simple effect on motion around the rims. It does not pull from within, it allows pull from outside to dominate. The result is a pattern that looks like a gentle outward push at the edges, though it is gravity acting from elsewhere. Groups that skirt a hollow feel less tug from inside and more from adjoining sheets, so their paths bend away from the center. Velocity fields built from independent distance measures show this behavior clearly in select directions. Coherent components point outward from the heart of a deep underdensity, and a line along the rim where lanes trace the border. The pattern persists across separate indicators, which means it is not a trick of one method. The subtraction of pure expansion has been handled carefully, and the remainder signals where mass is missing as much as where it gathers. When a rich district sits on one side of our region and a broad hollow lies on the other, the two together shape the vector we infer against the background glow. Attraction pulls toward the crowded side. The deficit on the opposite side removes opposing leverage. The measured flow is the combination. This dynamic interacts with late-time acceleration in a way that matters to the long story. As expansion speeds up, material near the outskirts of a hollow finds it harder to turn around and fall inward. The contrast between walls and gaps sharpens. Over very long spans, the hollows grow larger, measured by the average separation of galaxies, and the lanes take on cleaner edges. Flows along those edges keep their direction because the map itself is clarifying. Remote structures lose leverage faster than nearby ones, but the local routing remains stable. The quiet message is that the shape of underdense regions is not fixed by chance. It deepens with time and steadily steers what passes alongside. Observations in several bands support the picture drawn from velocity fields. Surveys that count gas-rich galaxies find very few within the deepest parts of certain hollows. Catalogues that track older stellar populations do not suddenly rise when slicing across the same volumes. High-energy maps that would light up compact knots remain smooth in those directions. Each absence has its own uncertainties, yet together they confirm that the tracts are truly sparse. With fewer anchors inside, paths around the perimeters are nudged consistently by mass that sits beyond. The steering does not come only from crowded nodes. It also emerges from the quiet parts of the map, where a deficit plays as much of a role as a surplus. There is a measured simplicity in this idea. You do not need a new force to explain the outward pattern at the rim of a hollow. You need only recognize that gravity responds to gradients. If one side is lighter than the other, motion favors the heavier side. The language of push is shorthand for a lack of counterpull. It is human to phrase it that way, because the sensation matches experience. On empty streets, a person drifts toward lit windows. In open sky, birds lean toward thermal columns that rise above warmer ground. Here, groups tilt toward lanes because that is where the field is lower. The analogy lasts only a line, yet it brings the idea close enough to feel, then gives the floor back to the facts. The concept of a broad underdensity opposite a crowded district becomes especially helpful in our region. It explains why the measured vector points with a steadiness that agrees across methods. The crowded side supplies a clear destination for streamlines within a certain range. The hollow reduces pull from the other side, keeping the lean intact. Flow reconstructions that include both features describe our motion with fewer arbitrary adjustments. They also predict how peculiar velocities should change for neighbor groups that sit at different positions along the rim. Those predictions can be checked by adding new distance measurements. When the checks succeed, confidence rises that the map is capturing the right balance. Late-time acceleration complicates dreams of ever larger unions but clarifies nearby routing. As the general expansion grows, distant assemblies lose the ability to recruit new members across very wide gaps. By contrast, existing lanes continue guiding groups already within range. In time, hollows grow to be more prominent in relative terms, because the spaces between dense regions widen faster than dense regions can shrink those spaces. The picture becomes one of islands linked by well-traveled channels, with broad, quiet seas growing between them. Motion along a familiar shoreline remains. Motion across the sea becomes rarer. For our purposes, this means the role of a nearby hollow in shaping present flow will not fade. It may become easier to see in the data as contrasts sharpen. For a calm listener, the start meaning is plain without being dramatic. A deficit can be as informative as a surplus. Where the map is thin, paths avoid the interior and trace the edge. Where the map is rich, paths converge from several directions. When the two settings face one another across our larger neighborhood, the combination sets a bearing that repeats through different catalogs. That repetition is worth resting upon. It says the steering of our path comes from both sides of the ledger, what is there and what is not. Gravity gathers what lies within reach. Over long time, it builds groups and clusters capable of holding members against general separation. The reach, however, is not unlimited. It depends on the background against which the gathering occurs. When matter dominated the energy budget, pull could win across larger spans, and growing structures expanded their domains. As the share of energy associated with empty space rose, the balance shifted. The expansion began to speed up, and the time available for distant regions to come together shortened. The effect is gentle in the present, but meaningful over very long stretches. It sets a limit to what can still assemble from far-flung tracts. On scales relevant to our measured motion, this leads to a nuance that matters. A rich cluster not far away can continue to deepen, drawing in systems from nearby lanes. A heavy district farther off can bias velocities here, because the gradient it imposes reaches across space. Yet the final act, implied by a simple line on a map complete merger of distant basins, becomes less likely as acceleration strengthens. The gradient remains, the path simply cannot be walked to the end. The story shifts from final union to present orientation. The direction we measure is real and steady. The destination, in the strict sense of everything joining everything, moves out of reach. Modelers express this change by how they allocate the pieces of our speed. Shares assigned to nearer nodes still matter, and they can lead to completed infall within bound domains. Shares assigned to deep districts frame the orientation of many routes, but do not guarantee arrival. The distinction is not decorative. It tells us how to read the vector against the background glow. The arrow describes where mass already sits and how it shapes the field. It does not promise that material here will one day enter the deepest well visible on the horizon. The horizon has its own rules, and one of those is a limit on how far. Influence can be translated into membership. Evidence for this background change comes from distance measurements that relate redshift to the brightness of standard candles. The relation is not what a simple, unhurried expansion would produce. It shows the fingerprints of acceleration over the last few billion years. That same era is when the largest structures would have needed more time to recruit from their outskirts if they were to finish. The recruitment continues where members already orbit within reach. It fades across very large separations because the fabric between those regions grows faster than gravity can close the distance. Within this frame, the attractor near the plane is best described as a broad basin that shapes present motion. It is not a harbor we will surely enter as a full assembly. Bound interiors keep what they have and refine themselves slowly. Paths far out stretch thin and begin to slip away. Over immense spans, filtration becomes stronger than collection, and regions settle into what they already contain. Our own group will continue its internal story, while the larger map keeps our orientation steady without promising a final arrival at the far basin. This is not a loss. It is a clarification that fits the tone of quiet science. A listener can rest on causes rather than chase endings that lie beyond useful horizons. The direction we measure teaches us about the mass field around us and the balance between local pulls and broad gradients. It does not need to resolve into a grand merger to be meaningful. The steady arrow still speaks. It speaks of how matter is arranged, how lanes guide, how hollows ease the lean, and how heavy districts tilt flow lines across wide volumes. It is also a reminder that scales matter. A person can think about family, town, and continent at once without confusing them. Gravity works with similar tiers. Bound interiors finish tasks within their walls. Corridors handle traffic between neighbors. Far districts act like weather patterns that set the general trend without controlling each street. Acceleration shifts what can migrate from pattern to pattern. It keeps local stories intact and slows the transfer between very distant settings. In that light, the idea that arrival is not guaranteed becomes a resting thought rather than a worry. The map is truthful as a guide to the present. It does not pretend to be a ticket to a single final address. A velocity field cannot be drawn unless distances are known independently of redshift. Several methods provide those distances, each with its own calibration and its own limits. In spiral galaxies, the width of the neutral hydrogen line offers a rotation speed. Faster rotators are, on average, brighter in total light. With the width measured, and with careful corrections for viewing angle and dust, the observed brightness becomes an estimate of distance. The relation is simple enough to apply widely and robust enough to survive moderate noise. It ties gas kinematics to starlight in a way that moves beyond redshift alone. Another method takes advantage of texture in the light of elliptical galaxies. In the nearest of these systems, individual bright and faint patches stand out. As distance increases, the patchiness smooths, not because the galaxy changes, but because the features blend together in the detector. By calibrating the pattern with nearby examples whose distances are anchored by stellar yardsticks, observers build a ruler that works across intermediate ranges. It is not tied to a particular kind of variable star or a rare event. It lives in the softly grainy surface of many ellipticals and can be applied wherever images are clean enough to measure the fluctuations. For nearer galaxies, individual stars make reliable rungs. Certain pulsating variables link their periods to their intrinsic brightness in a tight way. They act as steady beacons when crowding does not overwhelm them. Another rung comes from a sharp change in crest. The brightness distribution of old stars, where red giants exhaust one fuel and begin another, a clear cutoff appears. That cutoff is recognizable and consistent across many systems, and it acts like a step on the ladder that observers can place with modest effort. Both of these rungs tie the smallest scales to the wider map. Farther out, particular supernovae serve as lighthouses when the galaxies that host them already sit on the closer rungs. Their peak brightnesses, when corrected by simple properties of their light curves, are similar enough to compare across great distances. By linking hosts back to nearer benchmarks, observers extend the reach of distance estimates to ranges where individual stars are no longer resolved. The ladder then spans from close neighborhoods to the far outskirts of our mapping volume. Every rung supports those above and checks those below. None of these methods is perfect alone. Each carries selection effects and sources of error that can bias results if left unaddressed. In crowded areas near our plane, dust absorbs and reddens light in a way that masks true brightness. To counter this, maps built from wavelengths that trace dust emission help correct the attenuation. Viewing angle matters in rotating systems because widths change with inclination. Consistent geometric corrections are required. Samples that include only the brightest objects at large distances can fool statistics, so analysts model completeness carefully and test it by comparing subsamples. Redundancy is the main defense. Spirals and ellipticals live in different settings and respond differently to crowding. Agreement between their indicators is reassuring. Supernova hosts spread across lanes and along rims of hollows, distributing calibration so one structure does not dominate the result. Where overlaps exist, distances from one method are compared against those from another, and outliers are examined. The pattern that survives comparison becomes the backbone of the catalog. With distances in hand, redshifts can be decomposed. The portion expected from pure expansion is calculated from the distance. The difference between that and the observed recession along our line of sight is the peculiar velocity. A single remainder would tell little. Many remainders, spread across sky and distance, become a flow pattern. The pattern is then smoothed over scales appropriate to the data and compared with maps of visible structure. The fit is adjusted within modest bounds until the field hangs together without strain. When changes in calibration are made, the flow updates slightly, but does not swing wildly. That modesty is what we want in a sleepy channel, a process that is patient and cumulative. As instruments improve, parallax fixes the 0 point of the ladder more firmly. Interferometers measure line widths with smaller uncertainties across larger samples. Imaging at infrared wavelengths reduces confusion in crowded fields and pierces regions near the plane where optical counts suffer. Each improvement narrows error bars and makes the flow map cleaner. None overturns the general direction. They sharpen amplitude and clarify which regions contribute more and which contribute less. Over time, the catalogs refresh and the map stabilizes further. This methodical approach ties science back to a familiar feeling. People trust roads that are marked at regular intervals, with signs that match and lines that do not wander. The distance ladders play that role at cosmic scale. They do not shout. They stand at measured intervals and confirm what the last marker said. When a new sign appears, drivers do not slam the brakes. They nod and keep going. In the same way, each new rung on the ladder supports the one above it, and each comparison keeps the flow honest. The result is a set of distances that behave well under scrutiny, and a velocity field that guides the eye to the same gentle lean, again and again, without fuss. The broad plane of our galaxy complicates deep mapping because dust grains scatter and absorb visible starlight. The effect is called extinction, and it varies from mild dimming to near erasure. Some clouds act like thin veils, others are dense, cold knots. Relying on optical counts alone misrepresents what lies beyond those curtains. To correct for this, observers build foreground maps using measurements of dust emission at infrared and microwave wavelengths, and by comparing star colors to their expected dust-free values to infer reddening. With those maps, galaxy brightnesses can be adjusted toward intrinsic levels, and distances inferred from light become closer to truth. This is careful work done over large areas, because extinction is patchy, changing over small angles as filaments twist and clumps overlap along the line of sight. Even the color of the dust's glow matters, since warmer grains brighten in a way that can mimic structure if not modeled with patience. A second strategy is to sidestep the worst patches by switching the band of observation. Neutral hydrogen emits radio waves at 21 centimeters. That line passes through dust almost unhindered, so gas-rich galaxies behind the plane can be detected even when their stars are hidden. Large single-dish antennas sweep low latitudes, measuring line profiles and recession speeds. When a detection is cross-matched with sensitive infrared images, a faint stellar counterpart often appears. Its shape gives an inclination. Its integrated light, once corrected using the dust maps, supports a rotation luminosity distance. In this way, catalogs grow in places where optical work alone would stall. The coverage does not have the neat regularity of high latitudes, but it is real and repeatable, and it lowers the noise that once limited reconstructions of motion. Clusters announce themselves differently. Hot plasma trapped in their wells shines brightly in X-rays. That glow threads through obscuration because the energetic photons are less easily blocked by dust. Surveys that scan the sky for extended X-ray emission reveal massive structures even when their member galaxies are faint in ordinary light. Another tracer, the spectral imprint clusters leave on the background glow, adds depth. The signal is subtle but measurable, and it confirms where hot gas sits, even if the optical image is crowded by foreground stars. These signatures can be combined with weak distortions seen in background shapes to estimate total mass without relying on luminous members. Together, they build a picture of heavy nodes tucked behind our disk. The combination of these approaches shrinks the old avoidance zone from a forbidding band to a manageable slice. The slice cannot be erased entirely. Foreground stars still crowd detectors. Photometry near the plane remains difficult, and some sightlines saturate even infrared cameras. Yet the net effect is decisive. Flow reconstructions no longer bridge a blank sector with guesswork. They are anchored by real galaxies, with measured velocities, and by clusters whose wells are mapped independently of visible light. Where the old charts carried dotted lines, the new ones carry entries with distances and errors. Uncertainty remains, but it is quantified and shared between methods rather than inherited from one troubled wavelength. This progress changes more than the appearance of a sky chart. It tightens the link between peculiar velocities and the structures that cause them. When an X-ray halo lies exactly where the velocity field requires extra mass, confidence in both maps rises. When hydrogen detections align into a lane veiled to optics, a channel for motion becomes credible. These overlaps reduce uncertainty, because no single technique carries the whole burden. Each compensates for the other's blind spots with different strengths. Cross-checks become routine. Radio line widths against infrared inclinations, X-ray temperatures against distortions of background shapes, microwave spectral dips against catalogued clusters. The agreement does not need to be perfect to be persuasive. It needs to be consistent within understood errors, and it is. Practical details matter for calm accuracy. Dust maps must be calibrated against regions with minimal extinction. Foreground stars must be separated from distant giants by color and proper motion. Inclination estimates for spirals need consistent geometry, because small angle errors bias rotation widths. Radio beams must be wide enough to collect the entire disk, yet narrow enough to avoid confusion from neighbors. X-ray instruments must distinguish diffuse cluster glow from point sources. Microwave analyses must remove emissions from our own galaxy before the imprint of distant wells emerges. Each step has a checklist. Each checklist has a history of revisions that made later catalogs steadier. It is patient craft rather than sudden breakthrough. As catalogs deepen, the plane grows more transparent in practice. Infrared all-sky surveys record the steady glow of old stellar populations that are less affected by dust. High-resolution radio arrays map hydrogen with sharp beams that pick out separated disks even in crowded fields. Algorithms trained on stellar motions prune foreground stars from the background, leaving the extragalactic pattern cleaner. With every improvement, the corridor through our disk becomes less mysterious. The direction of our measured drift is traced by actual members rather than by inference drawn across blankness. Where a lane crosses the plane, objects appear along its expected line. Where a wall should continue, X-rays find it sitting where the velocity field predicts. There is also a shift in confidence that suits a sleepy listener. The once hidden sector becomes a place where multiple methods meet. A cluster seen in X-rays sits near microwave evidence of hot gas, and galaxies with radio profiles line the same path. Distances tied to rotation or to surface texture agree, within errors, with those estimated by standard candles in less crowded fields adjacent to the plane. The harmony is not perfect, but it is consistent across updates. Numbers change modestly as calibrations improve. Directions remain. The picture steadies. These gains feed back into models that reconstruct the local flow. Analysts no longer need to assign large weights to extrapolations across the galactic band. Instead, they input measured nodes, measured walls, and measured hollows. The velocity field bends where anchored mass dictates, swings past nearby wells, and leans toward a deeper basin beyond the first wall. When forecasts are made for groups tucked close to the plane, the predictions can be checked against fresh distances that arrive with each observing season. The habit of prediction and test is what turns a patchy sky into a navigable map. Every improvement carries an emotional echo of clarity. It feels like stepping from a bright window onto a veranda at dusk and finding your eyes adapt. Shapes that were suggestions become steady outlines. Paths you guessed are real lanes. In that gentler light, the story of the Great Attractor becomes simpler rather than larger. We are not adding drama. We are removing obstacles between the measurements and their causes, and the result is a calmer map. The plane is still busy, but it is not a wall. It is a filter we have learned to read. That patience is part of the promise. Light from the districts we track has traveled for hundreds of millions of years. Our effort to see through our own disk has taken decades. The match in timescales is not close, but the spirit aligns. Small steps accumulate, dust maps sharpen, radio catalogs grow, X-ray lists add entries where none existed. Microwave signatures are measured with cleaner baselines. With each addition, we trade a little confusion for a little confidence. Over time, confidence wins. The corridor remains complex. It also remains legible, and legible skies fold easily into rest. There are still careful caveats, and including them keeps the map honest. Neutral hydrogen can, in special conditions, absorb its own line, softening an otherwise crisp profile. Analysts flag those cases and avoid using widths that would bias rotation speeds. Near-infrared colors reduce reddening, but they do not erase it. Extinction coefficients vary with grain size, and must be tuned by longitude and latitude. Proper motion catalogues from precise astrometry separate foreground dwarfs from distant giants. Short baselines in radio arrays can filter out extended emission. Mosaics fill the gap. High-energy maps have backgrounds that drift over time. Blank field subtraction and repeat visits fix the drift. None of these touches the core conclusion. Together they preserve the quiet fidelity the flow map needs. Calibration also leans on yardsticks set close to the plane. Globular clusters with well-measured distances provide checkpoints where reddening laws can be tested. Open clusters add younger stars whose predictable luminosities verify color corrections. In a few narrow windows where dust thins, sight lines act like calibration slits. Galaxies glimpsed through them become reference beacons for the wider band. Piece by piece, the midplane stops behaving like a barrier and becomes a region with simple rules. The hidden becomes legible, and legible skies fold easily into rest. Astronomers once outlined very large associations by where galaxy counts rose across broad swaths of sky. Boundaries were soft, and a center was usually assigned to the brightest cluster in each region. The practice offered helpful labels, yet it did not always reflect how matter actually moves. A more instructive view defines neighborhoods by flow. In this view, a supercluster becomes a basin of attraction rather than a shape with fixed edges. Its extent is the domain inside which galaxies tend to stream toward a common gravitational focus once the average expansion is accounted for. The label describes what motion does today, not merely what brightness sketches across a map. To implement the idea, catalogs of distances are turned into three-dimensional velocity fields. The fields are smoothed over large volumes to mute small, noisy features and to highlight coherent gradients. Streamlines are then traced through the field, showing how a typical system would drift if allowed to respond to present-day forces. Regions whose streamlines converge on the same focal district are grouped, even if their footprints look disjoint in projection. This logic can unite branches once thought separate, and can split grand shapes if their parts fall toward different ends. The outcome is a set of domains whose definitions depend less on where bright knots sit and more on where motion leads. It is gravity's map, drawn with present vectors. In our surroundings, the flow-based picture reveals a single extended catchment with several major arms. One arm includes our group and the nearby rich cluster that influences current speeds. Another runs along walls that skirt the plane where dust complicates counts. A third reaches into deeper longitudes, linking chains that were difficult to follow before radio and infrared surveys filled the gaps. Farther out, these arms share a destination within the broader district that deepens the regional slope. The label for the catchment captures its size without implying perfect closure. Streams define it, fences do not. Defining neighborhoods by motion helps resolve mismatches between brightness maps and gravity's work. Counts can be high, where recent star formation boosts starlight without adding much mass. Conversely, an old population can look dim while sitting in a heavy halo. Flow fields care about the pull, not the sparkle. When a lane of convergence threads through a faint sector, it hints that obscured mass stands nearby. When streamlines diverge around an apparently busy patch, it warns that the light is not anchored to a deep well. In both cases, motion supplies the test that brightness alone cannot pass. Practical steps keep the approach modest and reliable. Smoothing scales are chosen to match the density of distance measurements. Two coarse and distinct basins merge on paper, though not in space. Too fine and noise pretends to be structure. Analysts test stability by changing the smoothing length and by masking sectors to see whether the main catchments persist. They also compare reconstructions built from independent distance indicators. rotation-based ladders for spirals, surface texture rulers for ellipticals, and standard candle anchors where available. Agreement across these families strengthens any claimed domain. Disagreement signals where additional observations should be aimed. The flow-defined domains are not static. As new measurements arrive, their edges shift by modest amounts. The shifts are not arbitrary. They tend to sharpen where catalogs become richer and to relax where coverage remains poor. This elasticity is a strength rather than a flaw. It means the method honors data rather than holding to an outline by tradition. It also prevents overclaiming. A domain's reach is drawn only as far as streamlines point consistently toward the same district. Where the pointing fades into noise, the pencil lifts. The map stays honest. For the listener, the benefit of this view is clarity. A basin of attraction is something the mind can hold gently. Water runs downhill without caring where paint was once brushed on a wall. In the same calm sense, galaxies drift along gradients built by the mass field regardless of which clusters glow brightest. If two bright knots pull in different directions, the ridge between them marks a divide. If several moderate nodes sink toward a broader depression, their neighborhoods are part of one domain. The picture is less about outlines and more about tendencies, less about names and more about guidance. There are also helpful consequences for how we interpret our measured vector against the background. When neighborhoods are defined by motion, our speed can be apportioned by domain rather than by arbitrary boxes on the sky. A nearby basin explains one share, and its center predicts how groups within it should accelerate relative to each other. A deeper basin explains another share and sets the overall orientation that remains even where membership will never materialize because of accelerating expansion. This language keeps the story honest. Present direction is shaped by several scales. Arrival belongs only to the ones that are truly bound. Counts still matter. They are simply seated in the right place. Lanes of high density, when traced with corrections for extinction, mark routes that flows prefer. Junctions where several lanes meet signal places where basins not. Yet it is motion that tests the idea. If streamlines refuse to converge on a supposed center, the center is misnamed. If they wrap around it and point somewhere else, the heavy focus lies beyond. In practice, those tests often vindicate maps that earlier work proposed, and sometimes they revise them with small, telling shifts that make later predictions work better. The redefinition also supports better forecasts. When updates to distance ladders alter distances by small percentages, the flow field changes in ways that can be predicted. Basin centers drift slightly. Divides tilt by a few degrees. Path lengths along corridors extend or shorten by modest fractions. None of these adjustments overturn the direction we care about. They refine it, and they let modelers state clearly how sensitive a given conclusion is to calibration. The statement, repeated softly, is a comfort. Orientation is robust. Details respond to better light. Closer to home, the motion-based neighborhoods describe how our group relates to the larger structure without promising arrivals that lie beyond practical time. Our arm bends toward the nearby cluster because the gradient is steeper in that direction. Beyond that bend, the arm aims toward the broader district that sets the regional tilt. The two relations coexist. The first governs dynamics inside the near domain. The second frames orientation across the wider field. A person can live in a town and still be influenced by the prevailing wind that blows across the countryside. Both truths can be held at once. There is one more gentle gain. By highlighting the domains where motion truly converges, the method points to where multi-wavelength observing is most useful. A suspected center that lacks X-ray glow invites deeper exposure. A corridor that appears in radio surveys but not in optical counts suggests a dust correction to test. Conversely, a bright patch that fails to attract streamlines may not deserve extended weight in models. Time and attention can then be placed where they pay the greatest clarity dividend, which is a quiet, practical mercy in a field with finite nights and finite instruments. Some researchers describe the procedure with the language of watersheds. The velocity field plays the role of a landscape, and the streamlines are imagined rivulets. Divides trace, where motion separates toward different centers. Basins mark where paths collect. If a supposed divide shifts wildly with small changes to inputs, the underlying data may be too thin there. If a center remains fixed across trials, it is probably real. The picture becomes intuitive without losing discipline, and that helps keep updates calm, even when catalogs change. Another quiet strength is that flow domains cut through the bias of projection. Two clusters that seem adjacent on the sky can sit far apart in depth. A lane that looks broken by foreground stars can be continuous in three-dimensional space. By working in distances and velocities, the reconstruction honors that geometry quite gently. It prevents false unions and restores links that dust had hidden. The result is a map that matches how gravity acts, which is three-dimensional. It is a small shift in language that yields a large gain in understanding. In the end, redefining neighborhoods by motion does not change the universe. It changes the way we draw it, so that the drawing honors what gravity is doing today. The approach accepts that names will evolve, that borders will soften or sharpen, and that labels are tools rather than trophies. For a channel that values rest, this philosophy feels right. Accuracy achieved without insistence, boundaries that flow from causes, a map that grows clearer as measurements accumulate, and a listener who can let the thought settle like evening air. Evidence about our motion lives in many instruments that do not speak the same dialect. Maps of the background glow are gathered by space telescopes with different detectors, beams, and scan patterns. One mission drifts slowly and builds depth by repetition. Another covers sky quickly and smooths noise by design. Their pictures of tiny temperature variations agree in broad strokes and differ in small textures that matter to careful fits. Distance ladders lean on parallaxes that are revised when baselines lengthen and calibrations tighten. Rotation widths recorded in older receivers are remeasured with better stability and cleaner band passes. None of this is scandal. It is the normal way numbers ripen. Speeds quoted a sit. Decade ago move by small fractions when 0 points shift. Shares assigned to near and far contributors are rebalanced as catalogs widen. The direction survives these nudges because it is not held by a single pillar. It is supported by many, and each pillar carries part of the load. Some claims push farther, proposing motions on scales so large that ordinary structure growth seems too weak to explain them. Analyses search for subtle alterations in the background glow, where it passes through clusters, hoping to isolate imprints of coherent drift, spread across vast distances. The signal is faint, and the subtraction of foregrounds is difficult. One team's map suggests a slow slide in a particular quadrant. Another team, using the same sky with a different pipeline, does not confirm it. The tension draws attention out of proportion to its influence on our local story. Whether or not those very large hints endure, the velocities that matter for our surroundings remain rooted in distance comparisons and multi-wavelength structure maps. The guidance toward a broad basin beyond the first wall and the deflection near the closer knot are present without leaning on controversial extremes. Revisions come from quieter corners too. Parallax catalogs sharpen the positions and distances of nearby standard candles. A handful of calibrators move by small amounts. The revised 0 point climbs through the ladder adjusting distances to hosts that anchor rotating spirals and grainy ellipticals. A relationship between line width and brightness tightens when profiles are measured with finer channels and cleaner baselines. Surface texture measurements adopt improved treatments of sky background and detector response. Each tweak shifts individual entries by a little. 1,000 small tilts smooth out into a field that is recognizably the same. The field keeps its gentle lean through the corridor and into deeper longitudes. The emotional lesson is steadiness. You do not need to brace. For whiplash every time a catalog updates, you can let the picture grow clearer at a pace set by the sky. Disagreements that do matter almost always trace to systematics rather than to the sky itself. Dust corrections near the plane can imprint spurious gradients if maps of foreground emission are mismatched in resolution or not tied to reliable color excesses. Selection effects can favor brighter galaxies at larger distances, biasing average properties unless completeness is modeled as a function of flux and surface brightness. Beam confusion in crowded radio fields can double count or blur line widths. X-ray surveys can misclassify point sources as diffuse glow without careful filtering. Microwave measurements must subtract our own galaxy's emission before faint cluster imprints emerge. Each hazard is well known, and each is met with methods that have matured through repeated use. The number of ways an error can masquerade as a flow has shrunk as independent teams test each other's steps. What remains after those tests is a direction that reappears across techniques, instruments, and seasons. There is debate about how far the relevant basin extends and how much mass lies beyond the district that already seems heavy. The edges of maps are not physical borders. They are limits of exposure time, sky access, and sensitivity. As new surveys deepen, counts of member systems rise in regions that once looked quiet. Weak distortions of background shapes refine the distribution of mass without caring about starlight. Hot gas appears in extended arcs that signal where intersecting flows have been compressing matter for ages. Each of these discoveries nudges the estimated contribution of distant structures by a little. None overturns the conclusion that our present lean is shared across volumes wider than a single cluster, and that influence is layered through nearby knots and deeper districts. It helps to remember that patient evidence fits the subject, light from the NTS. Wells we track has been traveling toward us since long before written language, and often since before continents settled into their current shapes. Our instruments have been improving for less than a human lifetime. There is no race here. A revised parallax, 0 point, a cleaner rotation width, an X-ray map with better background subtraction, each is a step that pairs well with a calm channel. You can hear the steps without feeling jolted. You can trust that a map built from many small improvements will be more dependable than a map assembled in a rush for spectacle. Confidence is not the same as certainty. Confidence means repeated tests point the same way, and different tools agree within understood limits. Certainty demands that no alternative remains, and that is not how sky work proceeds. Instead, teams publish flow fields with quoted uncertainties that reflect how sensitive each region is to calibration and coverage. They show where streamlines are robust and where they fray. They invite others to check with different ladders and different wavelengths. Over time, the frayed edges retreat, and the robust parts expand. The lean toward the hidden longitudes survives this process because it is fed from several sources that do not share errors. That is what you want when the subject is subtle. When claims about enormous, coherent motion surface, the community weighs them kindly but carefully. Do they persist when foregrounds are modeled differently? Do they shrink when clusters are selected in a more uniform way? Do they remain when the background glow is filtered with alternate windows? The answers have often favored restraint. Hints fade under improved control of systematics. That is not a loss for the story we tell at bedtime. It is a relief. The narrative does not need extraordinary reach to feel large. It needs harmony among instruments about what affects us here and now. Harmony, rather than crescendo, is what the instruments keep producing. You could think of this as the difference between weather and climate for instruments. Short-term swings in calibration look dramatic when isolated. The long trend of agreement looks calm when you stand back. We stand back here. We take the long view that shows a corridor through our own disk becoming legible in many bands, a bend near a heavy node shaping nearby flows, and a broader basin beyond that node biasing directions across a wide field. We accept that absolute amplitudes will be tuned as ladders tighten. We accept that shares assigned to each contributor will shift by a few % when catalogs grow. These are motions within the map, not motions of the map itself. Patience is its own result. It lets the listener rest on processes rather than chase headlines. It aligns with the way the sky moves gradually, predictably, and without concern for our calendars. When the next release of distances arrives, the flow will be remeasured, and the lines on the chart will breathe by small amounts. The breathing is welcome. It keeps the picture alive without changing its face. The evidence for a graded valley that guides our group remains, and the debate that attends any subtle measurement remains civil and cumulative. That is enough to set the mind at ease, as the thought drifts forward into the long future that follows. Close to home, the story that stretches across the longest spans is told by the largest members of our collection. Their mutual gravity ensures approaches and passages that will reshape stellar disks and tilt orbits. Gas will be compressed along tidal structures, and fresh stars will kindle where clouds are squeezed. The combined potential will deepen as luminous matter settles and dark halos blend into a common envelope. The timescales are vast compared with any human measure, but they are ordinary when set against the age of space. Over those spans, the steady brightening of our own star will raise temperatures in nearby worlds, and the outer parts of the group will continue to feel a gentle bias in one direction, because the larger field still tilts that way. Beyond the group, the nearest rich cluster remains a steady influence on present speeds. It supplies a downhill grade for groups within a certain range. Many systems closer to that center will sink deeper as time passes, joining subclusters and thickening the core. Our collection sits farther out, traveling within a corridor of the larger field without being guaranteed entry into the cluster's interior. This is not a contradiction. It is what motion looks like when acceleration sets limits to how far influence can be translated into membership. The grade remains. The path lengthens in a frame that favors completion for nearby travelers and gradually denies it to distant ones. Farther still, a broader district beyond the first wall continues to bias directions over a wide region. Its mass is distributed across overlapping wells and the lanes that bind them. It acts on us in two ways. It pulls directly with a long reach that shows in our velocity field. It also draws on nearer nodes, bending them slightly toward its interior and passing along a faint deflection to everything upstream. This layered influence is ordinary gravity working across scales. It is not sharp. It does not need to be. Gentle slopes integrated over long times produce measurable leans. Those leans show up when redshift is compared with distance, and they survive when distance ladders are recalibrated. Filaments that feed heavy nodes evolve as their reservoirs change. Along some lanes, material continues to move inward from less crowded regions, replenishing the cores of groups and clusters that already hold what they have. Along others, the supply dwindles as expansion carries matter beyond practical reach. Where supply persists, bridges between neighbors thicken, and substructures merge slowly. where supply thins, spans stretch and dilute. The contrast between busy corridors and broad open. The regions grows. The map becomes cleaner in outline, even as the number of active mergers declines. What remains at late times are islands of mass with strong interiors, linked by a few channels that still carry traffic, surrounded by wide tracts that contribute little new material. For our group, internal evolution dominates the tangible future. The largest spirals will experience several slow passages that raise plumes of stars and diffuse them into a swelling halo. Gas reservoirs will be stirred and, in places, consumed. Luminous arcs will fade as their brightest members age, while long-lived stars preserve a record of the dynamical changes. The combined system will settle into a shape governed by the blend of initial spins, encounter geometry, and the mass profile inherited from the halos that came together. The process has been simulated in many variants. The broad outcome is consistent: a single, more massive galaxy with a deep central potential and extended stellar envelope. That local destiny does not erase the orientation set by the broader field. Even as our group consolidates, its center of mass continues to move relative to the background frame in a way that reflects the larger gradients. The motion does not promise arrival at the deepest visible basin, but it remains a measurable marker of the field's shape. In a far future, when other structures recede behind horizons set by acceleration, this marker will become one of the few large-scale facts still accessible to inhabitants who measure motion against the background glow. The glow will be dimmer, and the catalogue of visible galaxies shorter, yet the frame it provides persists. Within that frame, a merged remnant drifts with a speed that remembers where the wider mass once lay. Observations that revealed this context will continue to improve, while such measurements are still practical. Parallax baselines will extend, fixing distance rungs with smaller uncertainties. Interferometers will gather line profiles for more gas-rich systems along the plane, and imaging in bands less troubled by dust will refine surface brightness textures in crowded fields. X-ray surveys will deepen maps of hot plasma in cluster wells that sit near the direction of our lean. Weak distortions of background shapes will be measured with greater precision, tightening mass estimates independent of starlight. Microwave analyses of the background will continue to refine tiny anisotropies while keeping the large dipole steady. Step by step, the catalogues will grow, and with them, the flow reconstructions will be refreshed. In the same era, models that reconstruct motion by minimizing transport cost under gravity will be fed with cleaner inputs. Their uncertainties will shrink near the plane and at the distances where new surveys add depth. They will continue to show a nearby knot shaping local curves and a broader basin beyond the first wall, setting the general tilt. The share assigned to each will evolve within error bars that are quoted and tested. The updates will not unsettle the story. They will confirm its patience. There is comfort in letting the long view stand without forcing it into a single dramatic event. The attractor remains a useful word for the graded valley that biases motion here and now. It is not a promise of arrival on the grandest scales. It is a description of where the field descends. Our group will continue its internal path toward a single, larger system. Neighbor groups inside the nearer basin will deepen their bonds. Corridors will simplify. Open regions will grow in relative terms. The far district will keep exerting a quiet, directional influence without closing the span. A person can think of this as a landscape at evening. Hills are visible, and the slope of the ground can be felt underfoot. The air cools, and sound carries farther. You do not need to reach every hill to know which way the terrain leans. You can accept the lean, set your pace, and move with confidence that the ground does not trick you. In the same calm sense, the flow field is a landscape we feel through numbers. It says, with steadiness, that motion is guided by familiar gravity, that structure has arranged itself into knots and lanes, and that a broad valley directs us without insisting that we enter its deepest part. That is a fitting frame for rest. Motion in space is not noise. It is a quiet contour that becomes visible when distances are measured in ways that do not depend on redshift alone, and when many wavelengths agree about where mass sits, even behind our own disk. Compare each galaxy's expected recession from expansion with its observed speed, and a remainder appears. Plot those remainders across sky and distance, and a field emerges that bends past a nearby knot and leans toward a deeper district beyond the first wall. The shape is not a straight path, and the destination is not a single point with a neat border. It is a region where matter has gathered across scales, and where roots align in response to a slope built over long ages. In this frame, an attractor is best understood as influence rather than appointment. It explains why our present speed, relative to the background, has a stable orientation across instruments, catalogs, and corrections. It clarifies why that same orientation need not culminate in a merger across the largest spans, because acceleration limits the reach of distant unions while leaving local ones intact. Regions already bound continue their slow assembly. Corridors maintain guidance for those within range. Wider basins remain causes rather than finishes. The distinction frees the mind from needing an ending and invites attention to the measured present. The hidden sector of our sky no longer forces extrapolation. Dust maps tuned by infrared and microwave data correct for reddening. Neutral hydrogen surveys pick out gas-rich disks behind the plane. X-ray maps reveal hot plasma sitting in deep wells, even where starlight is crowded. Weak distortions of background shapes trace mass without caring how bright it is. Together, these threads shrink the old avoidance zone and turn a confused strip into a navigable corridor. The corridor carries real detections with measured velocities and distances tied to independent ladders. Where dotted lines once stood, entries now carry uncertainties that can be weighed. Defining neighborhoods by motion rather than by counts gives those entries a context that matches gravity's work. Smoothed velocity fields show where streamlines converge, and those convergences outline basins with several arms. Our arm includes the local collection and the nearby knot that bends roots. Other arms skirt the plane and reach into deeper longitudes. Farther out, the arms bias toward the same broad district. Names are less important than tendencies. Streams define the shape, labels follow. Debates remain at the edges, as they should. Background maps differ in fine texture. Distance, 0 points adjust. Line widths are remeasured. Claims of enormous coherent motion are tested, and often soften when foregrounds are modeled better. These changes move numbers by modest fractions, without swinging the field. The direction persists because it is not owed to a single technique. It rests on overlaps that do not share errors. In that overlap, confidence grows at a pace that suits the subject and the mood. The long future holds separate layers. Inside the local collection, encounters among the largest members will reshape orbits and stir gas into new stars. Within the nearer basin, groups already within reach will deepen their ties. Across the wider region, the broad valley will keep its quiet sway without promising that everything will meet at its floor. Filaments will change as reservoirs alter. Open regions will take more of the map by proportion. The background glow will continue to provide a fixed reference against which motion can be measured while it remains reachable to careful instruments. In that frame, a merged remnant will still drift with a speed that remembers the larger layout, even when the view has thinned. For tonight, that's enough. Hold the shape, not the miles. A nearby knot bends the path, and a deeper valley beyond the first wall gives the field its quiet lean. Open regions ease the pull, and across many kinds of light, the corridor stays clear. What remains after expansion is subtracted, becomes a gentle guide gravity, doing what it always does, softly, in an ever-widening space. You don't need to reach the valley to know the way the ground leans. The numbers are honest, the instruments patient, and the picture steady across every method. The road we sense is real, the pace is kind. Trust the cause more than the finish. Good night.